Okay, guys, welcome. So today we're going to talk about some methods for solving systems in higher order ODEs numerically. All right. So one thing that I would recommend is that if you haven't already, I would view my video on numerically solving first order ODEs or singular ODEs, right? But anyway, let's go ahead and we'll move ahead. So when we say that we have a first order system of ODEs, we just mean that we have sort of a y vector of equations that we are considered with. In component form, it looks like y1 prime through ym prime. And we have each equation equal to some function of f, right? So y1 prime is equal to f1, y2 prime is equal to f2, so on and so forth. And then we have this vector of initial conditions, right? So you're seeing that sort of in component form here, right? Now here we're going to assume that f allows the system to have a unique solution. So you're getting that the solution exists there and also that that solution is unique. So we're basically assuming that all of our f functions are as continuous or smooth as they would need to be. Right? Now, before we talk about some solution methods, we should note that if you have a single nth order ODE, right? So if you have a mth derivative of a variable y equal to some function of the lesser derivatives, you would then need m initial conditions, right? So of course we could see the connection there by just noting that we could convert this to a system of first order ODEs by using methods that were previously discussed, and really that's just equating y1 to y, y2 to y prime, and so on and so forth. All right, so then of course we get the system given by these m equations and the corresponding m initial conditions. All right, so that's sort of some background information. Now, the first numerical method that we're going to talk about is, once again, the Euler method. And one thing to keep in mind about the Euler method is that just as in the single ODE case, it's not accurate enough to really have any practical purposes, but it's something that we're going to go through so that we can sort of get a feel for what this looks like for systems, and then we can sort of extend that to better, more accurate methods. All right, so the first example that we're going to look at is our familiar damped mass spring system. In this case, we're looking at the unforced or homogeneous version. So of course, we will have two initial conditions, and the step size that we're going to consider is h equal to 0.2. Okay, so now in a single ODE version, we obtain the next y value with this formula. Essentially, you're taking the local linear approximation to find your subsequent y value. So you would do y n plus 1 would return, well, in order to get y sub n plus 1, you would take yn and then add h times your f, or your derivative of the previous point, right? So of course we can easily adapt this to systems as long as we're now taking our vector of yn plus 1, vector of yn, and our vector of f equations, right? So in component form, what does this look like? It looks like in your first equation, right? So the first subscript indicates what equation we're in, and the second subscript indicates sort of which term that we're ending up with in our sequence, right? So of course, the first equation, you have the nth component of the first equation, and then you would add that to h times f1 evaluated at all of these nth components, right? And of course, a similar thing will hold for, all the way out to n equations. All right. Now, if in our given system, right? We're looking at y double prime plus 2y prime plus 0.75y equals 0. Now, if we let, of course, here the idea is that we're letting y1 equal y, y2 would equal y prime, and then therefore y2 prime is equal to y double prime. We can convert this to a system where we have that y1 prime is y2, and that y2 prime is negative 2y2 minus 0.75y1. And of course, that can be found by renaming these variables and then isolating y double prime by itself. Now we're gonna also consider the right-hand sides of each of these functions as f1 and f2, right? So now if we sort of apply this to the Euler method with h equaling 0.2, then we arrive at the following sort of recurrence relation for each of our two ODEs, right? So in the first one, we take the previous y, and then our function is just y2, and we're multiplying that by our step size h. And in the second equation, we're multiplying our step size h by now the function that we're denoting by y2 prime. So this is like f2, and this is f1. All right, so that's where those things are coming from. Now, of course, if we use the initial conditions, that's what allows us to calculate this thing, right? So of course, the first initial condition was that y0 is equal to 3, but y0 is evaluating y1 at 0. So we have sort of an initial condition there of y1 of 0 is 3. And then of course, if y prime is 0 is negative 2.5, that's saying that y2 of 0, since that's y prime, is negative 2.5. All right, now just for the sake of time and also for the sake of sanity, we're going to just summarize what you would get for the computations in this table. All right, now you can see that the exact solution is given here, right? And of course, this column is representing your error terms. Right, and then a similar situation is going on here, and these are your error terms. All right, so you can see that fairly quickly you're only getting accuracy to about 2 decimal places, which is okay, but of course we've only extended this to an x value of 1. So of course, if you wanted to go much further than 1, you could see how the error would start to grow and grow, right? So again, this is just a sort of as just a reminder, just for the single ODE case, this method is not practical because you pretty quickly get fairly significant inaccuracies, right? But we're just using this to sort of motivate the idea of solving a system numerically, right? Now this system is one where you could solve fairly easily using methods that we previously discussed, and you could find that your solution would of course be in this form. Okay, so that's sort of a brief introduction with the Euler method. Okay, now we're going to discuss a method that's much more useful, and that's by that's by using the Runge-Kutta method for systems of ODEs here, right? Now, and again, when I say Runge-Kutta here, we're assuming that we're doing a fourth order, which is often said to be RK4 as well. All right. Now, again, if you recall from our previous videos, sort of the idea behind RK4 is we compute these 4 sort of auxiliary quantities, right? So we compute these first. And then using those auxiliary quantities, we obtain the next value of y by taking the previous y value and then adding sort of this weighted average to it. All right, so let's go through an example. It will sort of allow us to talk about what's going to happen here with something like this. All right, so now what we're going to consider is we're going to consider the initial value problem, which is a demonstration of Airy's equation and the Airy function. So what I want you to consider is don't worry about this gamma stuff. we're just going to think of our initial y0 to be this decimal number, and we're going to think of our y prime of 0 to be this other decimal number. So don't worry about the cube roots of 3 and the gamma functions there. We're going to essentially just consider those decimal numbers as our initial conditions. Okay, so if we want to solve this using the Runge-Kutta method, we are, of course, going to convert this to a system of ODEs, which if we do so, we're going to let y1 be equal to y, and then y2 will equal y1 prime, which is, of course, the same as y prime. And then if we do that, we get this system here. All right, so just as in the previous example, we're going to let our right-hand side equal our f1 and our f2. And of course, we'll take our initial conditions into account. We know that y1 evaluated at 0 is this 0.355 number. And of course, our y2 of 0 is this negative 0.25 number. All right, now in the earlier method here, we said that each of these auxiliary quantities are K1 through K4. But just to cut down on subscript notation, I'm going to call K1A, I'm going to call K2B, K3C, and K4D, so that each of these values are essentially a two-component vector, right? Because for my K1, I have a system of 2 equations that I need. For K2, I have a system of 2 equations that I need. So this will just help us to cut down on some notation. All right. Now, if we compute these auxiliary quantities, we get that A is going to be H times this vector. We get that B is H times this vector. C is H times this vector. And D is H times this vector. Now, I want to show how you could get one of these components here, just so it's not seemingly completely coming out of nowhere. And if the first one that's really maybe not clear is that second component of B. So I want to talk about how you could get that, and then you could use a similar argument to get the rest of the components, right? So you could find the second component of B by doing the following procedure, right? So you know that F2, which is your right-hand side of your y2 prime, is x times y1. Now, in your B component, your first component is your x value, which is given by xn plus 1/2 h in this first auxiliary quantity, right? Now, the second component in this B vector is the y vector, which is given by yn plus 1/2 of the a vector, all right? And of course, the first component of this thing is just replace each of those vector components with the first subscript, right? So of course, now this x times y1, we now have that x is given by this xn of 1/2 times h, so this is where this is coming from, that's x. And then we just said that y1 was y1, the first component of, well, we should say y1 comma n plus 1/2 a1, right? And of course, you could follow a similar process, and then that would get you the remaining components sort of in all of these auxiliary quantities. Okay. So finally, of course, once you have all the auxiliary quantities, that's the hard part. And of course, we know that y sub n plus 1 is yn plus this weighted average of those auxiliary quantities. Okay, so again, just for sanity's sake, we're going to show that here's what you would get, right? So you can see now that in the Runge-Kutta method, you're much more accurate, right? So it looks like this is accurate all the way out to, for example, if you look at the error of y1, this is on the order of 8 decimal places, right? So that's pretty good, right? So this is obviously much better than Euler, much more accurate. All right, and of course that's good. Okay, so And for the most part, at least in my experience, most of the time that I have done any sort of numerical solving of system of ODEs, it's typically been with RK4. So that's a fairly common procedure to numerically solve these things. Okay, now I want to talk about sort of an extension of a Runge-Kutta method, which is known as a Runge-Kutta-Nystrom method, right? So this is basically just an extension of a Runge-Kutta method, only now we're taking out to one more additional component. We're now taking it out to y double prime, right? So again, we're still calculating sort of these four auxiliary quantities here, right? So still find these auxiliary quantities. And then once we have these four values, we're going to compute now a slightly different weighted average, right? So we have something that looks like this, right? And then if you, of course, if you take the derivative of this thing that we'll need in the next step, we get this relation here, okay? Now, if you have a y double prime just equaling some function of x and y, in other words, there's no y prime term, then of course you have K2 and K3 will become equal, and that will really cut down on your computational time, as we'll see in just a second here. All right. So again, you can see that you sort of have one less component to deal with. Okay. So we're going to look at just a quick example of this. We won't sort of go too much into the gritty details of it, but the idea is that if we were to look at the same example we just looked at, and we choose our h to be 0.2 as we did before, then we get that K1 is simply just going to be 0.1 times xn, yn, right? And then you can find these other auxiliary quantities based on that information, and you get that the error is about the same as what we did for Runge-Kutta, but obviously you're doing much less work here, right? So that's a nice advantage to this system here. Okay, one last thing that I want to discuss is what's called the backwards Euler method, and we looked at this a little bit before, but I want to sort of revisit it and look at what's called a stiff system, right? So just remember that when we did this before, when you have the backwards Euler method, this is an example of an implicit method, right? Because we're basically finding y sub n plus 1 implicitly here, depending on this equation, right? So you see that y sub n plus 1 appears on both the right and left-hand side, right? So this is an example of an implicitly found value, right? And of course, it's very similar to when we did this for a single ODE. Now, the advantage of looking at the backward Euler method is when you are faced with the possibility of losing stability for a certain type of problem, right? So the example that the notes gives here is that we say that for certain eigenvalue problems, if your step size goes past a certain value, so if your step size gets too big, what's going to happen is that you're going to lose some stability for this for whatever calculation that you're considering, and your solution, you'll see, will become very off very quickly. All right, so we'll sort of see an example of that in a table, but I want to go ahead and let's go through and we'll discuss this example with the backward Euler method. Okay. So we're going to solve the initial value problem where we have this non-homogeneous ODE. We have y double prime plus 11y prime plus 10y is equal to 10x plus 11 with our initial conditions of y 0 is equal to 2 and y prime of 0 is negative 10. right? Now you could verify using previous methods that the solution is e to the negative x plus e to the negative 10x plus x, right? But we're going to show this with backward Euler. Okay, so again, what would be the first thing you would do? You would convert this to a system of ODEs, so first order ODEs, right? So if you do that, we would then, of course, get y1 prime is equal to y2, and that y2 prime is negative 10y1, right, by moving the terms over. Negative 10y1 minus 11y2 plus 10x plus 11, right? And just converting those initial conditions to now our component-wise sort of initial conditions. Now, as a matrix equation, we could write this as y prime is equal to ay plus g, right? Because you have some sort of non-zero homogeneous term, non-homogeneous term there, we pick up a g vector. So your coefficient matrix is given by A, and then your g, of course, yeah, I should actually include this 10x in there too. Your g is given by a 0 in the first equation, but then you pick up that 10x plus 11 in the second equation. Now, if we find the eigenvalues of our coefficient matrix A, we'll find, of course, we should expect this, we'll find that our two eigenvalues based on, you should expect this based on the answer that we stated previously, you would find that your lambda 1 is negative 1 and your lambda 2 is negative 10. Okay, now if we apply our backward Euler formula to this, we get the component-wise sort of relationship as follows, right? So in your first equation, you find the n plus 1 term by taking the nth term and adding it to h times your, this is like your f1 here, evaluated at your n plus 1 term. And then your second equation has a similar sort of procedure, right? You're finding the n plus 1 term by finding the nth term and adding that to h times f2 evaluated at your n plus 1th term. Okay, now if we reorder this, right, we can get the following system, right, where if we move all of our n plus 1 terms to one side and our n terms to the right side, then we can arrive at this system here, right? So these are all your n plus 1 terms. And on this side, you have just n terms. Now, if we take our coefficient matrix and find our determinant, you'll find that you get your determinant is 1 plus 11h plus 10h squared, right? So if you form the coefficient matrix and you take that determinant, it's fairly easily to show that this is what you would get for your determinant. All right. And of course, you can use Kramer's rule, right? Sort of that formula where you have like the determinant and then replace your determinant with your sort of solution vector. You can find that explicitly you can get the n plus 1 component by following this formula, which only depends on the nth component, all right, which is now something that we can sort of calculate. All right. Now, if you look at the table here, here's what I want to show you for some of these things. Now, if you just look at these first two columns, this is showing you backward Euler method for two different step sizes. You have the step size of 0.2 and the step size of 0.4, right? And you can see that even though these answers at the bottom here for x equals 2, they're not exact, they are fairly close, right? They're accurate to the hundredths place, even though a step size of 0.4 is considered fairly large. Right, now if you compare that to the Euler method, even though we've used a fairly small step size, right, both of these step sizes are half of that of the backward Euler method, you're seeing that the values get pretty far off pretty quickly, right? And again, we're comparing this to sort of these exact values here, right? So you can see that the, again, so backward Euler for both step sizes is accurate to the hundredths place, whereas in the Euler method, for a step size of 0.1, you're accurate to the hundredths place, but for Euler step size of 0.2, you're not even accurate to the ones place, right? So you're fairly far off on that. All right, now even the Runge-Kutta method does not do well here, at least for the certain step size, right? Now, if you look at Runge-Kutta for step size 0.2, that's the most accurate of any of them, right? So you have the best accuracy here. But if you look at the next step size up, something interesting happens, right? So if you look at step size of 0.3, this is also the most off, right, of any of the values here. And that's because when you have the Runge-Kutta method, you're sort of, once you increase the step size past a certain point, you then lose stability of the accuracy of your numerical investigation, right? So that's where something like Backward Euler has an advantage, right? So this is where Backward Euler has an advantage in this regard. Okay, so one final thing is that we will look at what happens with the Euler method for h equals 0.18. And you see that you sort of have in the beginning part of this, you sort of have like this jumping back and forth for your solution points that Euler finds, right? And then it looks like after a while, you then start to converge to the solution. So this is sort of an example where you sort of you have a little bit of a stability problem in the beginning, but in this case, it looks like you do finally settle into the solution after a certain x value, right? Now, of course, depending on how bad it gets, you may not settle into a solution here, or it might even actually get worse as time goes on. All right, so that's sort of an interesting thing that can occur with sort of these numerical investigations. All right, but that concludes this video on solving ODEs, system of ODEs with numerical methods. I hope you enjoyed, and I will see you next time.